Okay. So far, we have been seeing probabilistic generative models, right? Where so the main idea behind probabilistic generative models is to model P of X comma Y, right? And often we would do this by modeling P of Y and P of X given Y, and then we would use the Bayes rule to compute P of Y given X, right? So one of the main okay. Why is it not working? It's weird. Okay, so one of the main limitation of at least the kind of generative models we have seen so far, right? Like is the fact that you need to make some assumption on what is P of X given Y. So with this with continuous models, we made the Gaussian assumption, right? It's with discrete models, we made the Bernoulli assumption, right? So you could think about different distributions that you want to like consider for P of X given Y. But the problem is you need to start your process by making this assumption. And once you make this assumption, it's fixed, right? Now, if your training data truly follows a Gaussian distribution, then GDA is going to have very high performance because it is making the right assumption, right? So what if my training data doesn't follow the assumption that I'm making? So how would that affect the performance? You're going to have a bad classifier, right? Because P of X given Y is not what you are trying to fit. If you're trying to fit a bad, like if you're trying to fit a wrong distribution, you're not going to get the best performance that you could get, right? In some sense, this idea of doing P of X given Y first, and then using the Bayes rule to compute P of Y given X, right, would work when the assumptions about P of X Y given Y is correct. Okay, now we are going to look at another class of another family of classifiers, okay, which are much simpler than generative models. Okay, so these are called probabilistic discriminative models. Okay, which is going to model P of Y given X directly instead of first computing P of X given Y and then doing the reversal. Okay, so this means I'm going to assume a model, like some mathematical model, which is going to approximate P of Y given X. The simplest way to do this is in binary case, we can just say, oh, the probability of class 1 given X is simply sigmoid of W transpose X plus W0. Okay. And learn the parameters W and W0 directly from data. Okay. So this is one of the reasons why I did those complex relations to GDA to fit GDA like this. Okay, so when we did GDA, so if you look at, remember the final equation of GDA, it was sigmoid of W transpose X plus W0. However, W and W0 were functions of mu, sigma, and all those things, right? So we had a complex equation for W and W0, which was further computed through the parameters of the Gaussian distribution. Is that correct? So now I'm going to throw away all those equations and say, okay, I'm going to assume that W is just some randomly initialized vector which means this W transpose X plus W0 is a simple linear model. Okay, so then I put a sigmoid on the top of the simple linear model. So the benefit of putting a sigmoid is like I'm getting a probability distribution, right? So we want, it's a binary problem, so we just want what is the probability in class 1 given X, right? So it's going to be something between 0 to 1. So sigmoid is going to give me some value between 0 to 1. So I'm doing sigmoid of W transpose X plus W0. Okay, so this is for 2 class problems, right? When you have k classes, then the probability of the class given X is given by simply softmax of W transpose X plus W0. This is when you have k class problem. Is that clear? So this really simple model, right, which takes a linear model followed by sigmoid or softmax, right? So this is called logistic regression, one of the popular machine learning algorithms. So logistic regression, we are going to do this for binary classification, okay? So you can extend it to, I think you are extending it to k class in your assignment, okay? So for binary classification, the probability of C1 given X is given by Y of X, which is basically sigma of W transpose X. So the bias is inside. Okay, instead of writing W transpose X plus W0, I'm observing the bias inside. So then the probability of C2 given X is simply 1 minus probability of C1 given X. Is it clear? Now, how many parameters does logistic conversion have? One. What? W? No, it's not one. So W is a vector, right? So what's the dimensionality of the W? So how many parameters are there in logistic regression? Yeah. So how many parameters are here? Yeah. What is T? What is T? So what is the dimensionality of the W vector?
Is it the amount of features?
Yes, it's just the number of features, right? Like, so you could make it M plus 1 if you want to consider the bias as well, but let's just say M parameters. Okay. Now compare this with GDA. GDA also looks exactly like this, except for the fact that W is parameterized by something else, and the number of parameters in GDA is order M squared. Okay, so when compared to GDA, logistic regression has much fewer parameters. Is that clear? Okay, now how do we learn these parameters? So we need an objective function, right? Oh, maybe before we go for our learning, a quick note about the name of this classifier, right? Like, so logistic regression is confusing because this is not a regression algorithm, okay? So we're doing classification, right? Like, so we call it logistic regression because it looks like a logistic function followed by like a linear model for regression, right? So this is as if I'm doing regression first, and then I'm putting logistic sigmoid on the top of the regression to get a value between 0 to 1. Is that clear? But this is a classification algorithm. Okay, now how do we learn the parameters? We need an objective, right? So what could be a good objective for what could be a good objective for a probabilistic model like this, but then like we are not modeling P of X comma Y, right? If you're modeling P of X comma Y, then you would just maximize the likelihood of the data set. You maximize the likelihood of each X comma Y var in the training set, right? Now, what would be a good objective for logistic regression? Yeah?
Least square.
Least square. Least square is, well, we saw why least square might not be good at like might not be good objective for a probabilistic model, right? So yeah.
What we're looking for is P of Y knowing X. Like that's our true objective.
Yes.
And the way we can approximate it at first is we just take the proportion. And we just find a function that gets us closest to that.
Okay.
Like my initial objective for me saying that is we want to get the joint distribution, the conditional distribution of Y knowing X.
So we are interested in P of Y given X, right? So that is what discriminative models are trying to model. Like, so like we want to somehow maximize the probability of Y given X for correct examples. So what we can do is take every example in the training set, and for each example, maximize P of Y given X. Okay, this is called conditional likelihood. Okay, so instead of the likelihood, which is P of X comma Y, I'm going to maximize the conditional likelihood.
Question?
Yeah.
What do we mean by maximize the likelihood or maximize the probability? Isn't that something that's out of our control?
No, yeah, okay. So when I say maximize the likelihood, it actually means find the parameters of the probability distribution that you're trying to approximate. Like basically, you're fitting a function, probabilistic function here, right? Like, so find the parameters of this function. In this case, find the W, which would maximize the probability, right? Okay, so conditional likelihood. So how do we define it? Let's take the data set. My data set is, let's say, x1, t1, x2, t2, right? Up to x n tn. So this is my data set. Okay, I have n examples in the data set. Data set has n examples. Okay, and the model y is sigma of w transpose x, right? Now, just as a recap, likelihood is defined as the probability of the data set given w, which is product of I is equal to 1 to capital M, P of xi ti. So that is likelihood, right? Now the conditional likelihood is given by probability of t given x and w, which is product of I is equal to 1 to capital N, P of ti given xi. Okay, and if you want to do log, then this becomes summation I is equal to 1 to capital N ln P of ti given xi. Is that clear? So this is the log likelihood. Okay, so I'm going to use likelihood and conditional likelihood interchangeably, but whenever we are doing mass integration, I say likelihood actually means conditional likelihood.
So is X an observation?
Yes.
And T is what class it belongs to?
Yes. Okay, so now when you do gradient descent, okay, first of all, so here it's going to be difficult to find closed form solution like what we did for GDA and Naive. Okay, so we're going to do gradient descent. Okay, so when you do gradient descent, like, so instead of maximizing the conditional log likelihood, well, you could do gradient descent if you want, but like traditionally we always do gradient descent. So what I'm going to do is just put a minus before this and minimize the negative log likelihood. Okay, it is same as maximizing the log likelihood. Okay, so what I'm going to do is to minimize NLL, which is the negative log likelihood, which is basically minus summation I is equal to 1 to capital N ln P of Ti given xi. Is that clear? Any questions? Okay, so let us do that and find the parameters. Yeah.
So what does NLN do again?
So this is just, okay, so instead of maximizing the log likelihood, I'm going to minimize the negative log. Okay, that's it. So that I can keep doing the same gradient descent. Okay, so let's compute the gradients now. So we are going to start with a data set, which is a bunch of x and tn. N is equal to 1 to capital N, right? That's where Tn K0. Okay. So the probability of T given W is given by product of n is equal to 1 to capital N. Okay. It's going to be Yn when the class is 1. Yn is just sigma of W transpose X. Okay. And it's going to be 1 minus Yn when the class is 1 minus Tn. Okay. If you think about it, I'm not making any assumption about what kind of probability distribution we are using here, right? So my probability distribution is just sigmoid of W transpose X plus W0 or sigmoid of W transpose X. Okay. So where T is basically all the targets T1 to Tn. Okay, and Yn is given by probability of C1 given Xn, which is sigma of W transpose Xn. Okay, so the error function that we are trying to minimize is minus ln P of T given W, which is basically minus summation n is equal to 1 to capital N Tn ln Yn plus 1 minus Tn ln 1 minus Yn. This is my error function. Is that clear? So now what we are going to do, we are going to differentiate this E of W with respect to W. You will get a gradient, right? And just do gradient descent using that. Is it clear? Okay, let's do that. So I'm going to copy. Let's do the next slide. Okay, so maybe I'll also write where Yn is equal to sigma of An, let's say, where again An is given by W transpose X. Okay. So now we are interested in dou E by dou W. Right? So we are interested in dou E by dou W, but E is not a function of W. So we have a recursive relationship here. Right? So E is a function of Y, right? And Y is a function of A, and A is a function of W. So when you want to do differentiation here, like so you're going to apply the chain rule of differentiation. Okay, so this is going to be summation n is equal to 1 to capital N, dou E by dou Yn, okay, dou Yn by dou An, dou An by dou W. Okay, so I want you to get comfortable with chain rule of differentiation because we're going to do this again and again moving forward. Okay, so like we will not have simple enough functions to differentiate. So once you have a little bit more complex functions, like where it is a function of another function, etc., so then you have to apply the chain rule of differentiation. Okay, so now we need to compute these three terms: dou E by dou Yn, dou Yn by dou An, and dou An by dou W. Individually, they are all simple like functions to compute. Okay, so let's start with dou E by dou Yn. So dou E by dou Yn is given by, okay, I'm going to do for just one example instead of the whole summation. Okay, so it's going to be minus Tn. When you differentiate ln Yn, you're going to get minus like by Yn, right? Plus 1 minus Tn by 1 minus Yn. So I'm putting a plus here because minus times the minus that is coming from the differentiation becomes plus. Okay, so this I can write as 1 minus Tn times Yn, okay, minus Tn times 1 minus Yn divided by yn into 1 minus yn. Okay, I'm just multiplying things and rearranging them. So this is yn minus tn yn minus tn plus tn yn divided by yn into 1 minus yn, and you can cancel these two things, right? So this becomes simply yn minus tn divided by yn into 1 minus yn. Okay, so this is my first term. So dou e by dou yn. Is it clear? So let's do the second term. The second term is dou yn by dou an. So dou yn by dou an, right? So what is yn? Yn is sigmoid of a of n, right? The sigmoid function has a nice form for its derivative, okay? So the derivative of sigmoid is just sigma into 1 minus sigma. Okay, so you can do the derivation to confirm, like, so it's basically sigma of an into 1 minus sigma of an. Okay, so the derivative of sigma dash is simply sigma into 1 minus sigma. Okay, so prove. Okay, I might ask you to prove this in a midterm, so try it. Okay, so sigma of an multiplied by 1 minus sigma of an. So sigma of an is simply yn, this is 1 minus yn, right? Okay, so now let's do the last one, dou an by dou w. So let's look at an. So can you tell me what is dou an by dou w? What is dou an by dou w? Yeah,
xn.
just xn. Okay, so it's just xn. So if you put all of these things together, so dou e by dou w is given by minus, sorry, there's no minus. So summation over n is equal to 1 to capital N, yn minus tn, okay, by yn into 1 minus yn times yn into 1 minus yn times x, yeah. So you could cancel these two things. So this becomes dou e by dou w is equal to summation n is equal to 1 to capital N yn minus tn times xn. Is that clear? Now this is my gradient for the logistic regression classifier. So once you have the gradient, then you could do stochastic gradient descent or full batch gradient descent or mini batch gradient descent, whatever you want to do. Okay. Now, does this look similar to the gradient that you had for linear regression?
Yes. The y minus when we had the y minus x xw. It's so similar.
Do you notice the similarity? It's actually exactly the same now. So even for linear regression, if you remember, the gradient was y minus target times xn. But for the bias, there was no x imposed 1, right? Like, so it would be same here as well. Right? It looks like they are both same. However, we started with different objectives. No? So for linear regression, what was our training objective?
Minimize the loss functions.
So what was the minimizing? What were we minimizing? Least squares, right? So we were doing least squares. If we were minimizing the squared error function for linear regression, right? If we were doing least squares, However, that is not what we are doing with logistic regression. With logistic regression, we are trying to maximize the log likelihood. So how is it that maximizing log likelihood and minimizing the square error function, like giving same gradient, right? Like, is it just a coincidence? So it so happens that there is some connection between maximum likelihood and least squares. That is why you see this similarity. Okay, so we're going to look at the relationship between maximum likelihood and the idea of least squares. Okay, so for this, we are going to go back to the regression problem. Okay, so we're going to go back to the regression problem, but we're going to take a probabilistic treatment of regression problem. Like, if you remember, when we did regression, we said y is just W transpose X, right? It was all deterministic. There was no probability involved in regression, right? So now we are going to take a probabilistic view. So I'm going to say that the target for regression is y of x given w, the deterministic part, plus some epsilon. Okay, so this epsilon mass is a Gaussian with zero mean and beta inverse variance or beta precision. Okay, so now I can talk about what is the probability of the target given x, even for regression. Okay, so for regression, what is the probability of t given x, w, and beta? It's simply the Gaussian with mean as y of x given w, beta. So this is like, I compute the deterministic target, then there's a Gaussian noise added to it. So the Gaussian is centered at y of x, and it has some values. Is that clear? So which means now I can also compute the conditional log likelihood of these predictions for the regression problem, right? Like, so given some data set of xn, tn, where n is equal to 1 to capital N, I can talk about P of t given x w beta as product of n is equal to 1 to capital N, a Gaussian, okay, with w transpose xn mean and beta inverse values. So I can also compute ln probability of t given x w beta as summation n is equal to 1 to capital N ln n of tn given w transpose xn beta inverse. Okay, so let me take this to the next slide. Okay, so this so if you substitute the density function for the Gaussian here, okay, so you will get something like this. So it's going to be n by 2 ln beta minus n by 2 ln 2 pi minus beta times ED of W, where ED of W is given by 1 over 2 summation n is equal to capital N Tn minus W transpose H the whole square. Okay, I'm going to go and do the substitution of the derivation. So just substitute the PDF of the Gaussian distribution here and do some simplification. Let's see, going to get this. Okay, so what does this mean? So when you are maximizing the log probability, okay, so these two terms doesn't have any parameters, and they are constants. When you are maximizing this, you are basically maximizing minus ED of W, which is this, right? Or in other words, you are just minimizing the square error. Okay, So this means that when you make the Gaussian noise assumption for regression, then maximizing log likelihood is same as minimizing least squares. Okay, so if I have to write this down, so maximizing log likelihood, right, is equal to minimizing least square. Well, I think it doesn't make sense. Least squares is already minimizing. Okay, so let's just consider the least square to be the name. Okay, so I'm minimizing least square. Okay, only when the noise is Gaussian. Is it clear? Okay, now let's go back to logistic regression. Now that we have learned the relationship between log likelihood and least square. So to recap, logistic regression is simply y is equal to sigma of w transpose x, right? Now, is logistic regression a linear model or a non-linear model? Someone else. Is it a linear model or a non-linear model? Or something else? Yeah. So what about GDA? What kind of model was GDA? Are you preparing for your midterms? So what kind of model was GDA? No, is it a linear model, non-linear model? Okay, what kind of decision boundary GDA
Linear.
has? Linear decision boundary, right? It is a non-linear model with linear decision boundary, right? So we named such kind of models as generalized linear models, right? Now, what about logistic regression? So how would the decision boundary of logistic regression look like? Linear, non-linear? By now, you should be able to look at it and tell whether the decision boundary is linear or non-linear. So at the decision boundary, y is going to 0.5, right? So sigma W transpose x is equal to 0.5. So W transpose x is equal to sigma inverse of 0.5, which is a linear equation. So the decision boundary of this model is linear, but the model itself is non-linear, right? So which means that logistic regression is also a generalized linear model. Is that clear? Yeah.
Just so we say that's linear because the d of e to on d of w gave us the y minus t times x, which is in the linear form. Like, is that what made us
So the decision boundary here is linear. So what do I mean by that is like, so where is the decision boundary for a binary classification? So y is equal to 0.5, right? So sigma of W transpose x is equal to 0.5. So the equation for decision boundary is this. Okay. Right? So this makes it a linear decision boundary, right? So generalized linear models, as I said in the last class, are still a little bit nicer than nonlinear models. Okay. So in fact, for logistic regression, so the error function of logistic regression, okay, is also going to be convex. Okay, yeah.
Just to make sure, because I'm a bit confused. So the logistic regression is a non-linear model?
No, it's a generalized linear model. Okay. So generalized linear models are nonlinear models with linear decision boundaries. Okay. So the loss function for logistic regression is going to be convex. Okay. So which means it's going to look something like this. And there is a single unique local minimum. So when you do gradient descent, you don't need to worry about local minimums here. Like you will reach the global plane. Is that clear? Any question? Yeah.
What did you say about the GLM?
Well, so they are still less complex when compared to fully nonlinear models. Okay, so like they still have some nice properties. For example, like the loss function here is convex. It's not convex.
It's a linear model.
It's a model with linear decision boundaries. So if you go by our definition of what is a linear, okay, what was the definition of linear model that we saw in the first class? So when would you say a particular model is linear? Yeah.
Respect to the parameter.
So it is linear with respect to the parameters, right? Like, so is logistic regression linear with respect to the parameters? No. You have a sigmoid of W, right? So that's why they are in between. Like, so these are non-linear models with linear decision boundary. So to differentiate them from non-linear models with non-linear decision boundary, which are way more complicated, we're going to call these as generalized linear models. They look non-linear, but they are still linear. Is it clear? Okay, so now we're going to use generalized linear models as an excuse to do a little bit more optimization. Okay, so like in one of the previous lectures, we looked at gradient descent in detail, right? So we're going to look at another iterative optimization method, okay, so which is called Newton-Raphson. Okay, which converges much faster than gradient descent when you have convex problems. Okay, so this is called a second order optimization method, like while gradient descent is a first order optimization. So why do I call it first order and second order? We're going to see that soon. Okay, but how many of you have seen Newton-Raphson before? Which are a few? So how many of you have done a numerical methods course? I know that at JGL, numerical methods is not a mandatory course for undergrads, but if you do computer science or computer engineering, you must learn numerical methods. Okay, so if you do numerical methods, like you would have seen Newton-Raphson in the numerical methods course, like, but I'm pretty sure you would see this in many other courses as well. Okay, so if you have not seen before, so we're gonna learn about it, so it's fine. So the main idea of Newton-Raphson is, as I said, like to use second order information. Okay, so gradient descent was using the first order information, which was just the gradient, right? So now we are going to use the second order information, which is the pulsation or the Hessian. Okay, so how do we do that? So to motivate that, we're going to start with the error function E of W, right? And I'm going to do a second order Taylor approximation on this error function. Okay, so I can approximate this error function at some point W0 by using Taylor series. Okay, and I'm going to do this for zeroth order, first order, and second order, and stop there. So this is going to be E of W0 plus W minus W0 transpose the gradient, okay, plus 1 over 2 W minus W0 transpose Hessian W minus W0. Okay, so this term that you see here, right? Got it. So this is the gradient. And this term that you see here, this is the Hessian. Okay, Hessian is basically dou square E by dou W square. Okay, so dou E by dou W is your gradient. Hessian is just the, like if you do one more differentiation of the gradient, you're going to get Hessian. Okay. Okay, so now let's use this as our error function. Differentiate this and set it to 0. Okay, so we're going to get, when you differentiate the first term, it's a constant. Okay, so it's going to be 0 plus, when you differentiate the second term, W0 is a constant, W is a variable, right? Like, so it's W times the gradient. When you differentiate this with respect to W, you're just going to get the gradient. Okay, plus W minus W0 transpose Hessian is equal to 0. Okay, so I'm differentiating this term with respect to W. There is no W in the first term, so that becomes 0. The second term, then W minus W0, we differentiate the second part goes to 0, but this is W times the gradient, so this is the gradient. So this is W square H, so 2 times W times H, right? That's what we have here. Okay? Yeah.
We differentiate on W or
Yes.
double? Okay.
W0 is a constant, okay? At a point W0, we are doing this. Okay, so this can be written as W minus W0 transpose H is equal to minus this. So W minus W0 transpose is equal to minus H inverse of, sorry, the gradient. Okay, so now I can bring the W0 to the other side. So this becomes W is equal to W0 minus H inverse of okay. So this is the update rule for Newton-Raphson method, right? Now the gradient descent update rule for you to compare against is W is equal to W0. Well, maybe let me write the Newton-Raphson as a general form. So the Newton-Raphson update is W new is equal to W old minus H inverse of the gradient. And the gradient descent update is given by W new is equal to W old minus alpha times okay. Okay. So what can you say about gradient descent versus Newton-Raphson just based on the equations? Hmm? So for gradient descent, well, they look almost same, except for the fact that gradient descent will be minus alpha times the error function. So alpha is your parameter, right? It's the learning rate. And as I mentioned earlier, this is one of the most sensitive learning rate in machine learning. Okay, so like how to find alpha, it's very tricky, right? Like so you need to try different values of alpha, and it's very painful, right? On the other hand, with Newton-Raphson, you don't have any alpha. There's no learning rate, right? So which means well, there's no hyperparameter to tune, right? Like so, however, alpha is replaced by H inverse, right? So what would, okay, gradient is a vector. Hessian is a matrix. Okay. Now the Hessian matrix, when you're doing another differentiation of the gradient vector, so what would be the dimensionality of the matrix? Let's say you have p parameters. P by p, right? Like because you're differentiating each with respect to everyone else, right? Like so you are going to get a p by p matrix, right? And you have to invert this p by p matrix. So what can you say about the computational complexity of gradient descent and Newton-Raphson? So which is faster? As in, okay, which is less compute. So which is faster is a has a different meaning here. Like so which uses more compute here? Yeah. Sorry?
This gradient descent.
Gradient descent is using more compute?
Oh, no, that's.
Okay, less compute, yeah. So here gradient descent uses very less compute, right? Like, so you're just computing the gradient, and then you're doing minus alpha is gradient. But the Newton-Raphson, you need to compute the gradient, then you need to compute the H. So that is already inverting the issue, which is another principle. And this could get very expensive as soon as the number of parameters grow. Right? So when the number of parameters grow, so neural interruption is both memory and compute inefficient. Because it also needs memory. If you have million parameters, then you're going to have million times million matrix. Right? So it's not going to be easy to do neural interruption all the time. Okay. However, if you can do it, like for example, in this case, let's say you have 100 features for logistic regression, and you can do Hessian computation, right? So then there's benefit because it's going to converge faster. Yeah.
The result is the same at the end,
Yes. So the result is the same.
but one is faster than the other. NR is faster,
Yes.
but more compute power to do it.
Yes. So that's why what is fast is subjective, right? Like, so let's say in theory, you have lots of compute available to you, and you care about finishing the experiment quicker. You can do that with neural interaction. Okay. However, if you're limited by memory of your RAM, then you cannot do neural interaction. So you just need to wait for whatever you can do with your gradient descent. Is that clear? Okay, so at the shallow level, it might look like neural interaction is not a very good idea, but we will revisit this once again, like in another optimization lecture, okay, and see how to make it more scalable. Okay, so for now, for the simple logistic regression problem that we are doing, neural interaction is okay. So we're just going to go ahead and do this. But before we do that, let's actually try to do neural interaction for linear regression. That's an exercise. Okay, so I'm going to do neural interaction for linear regression. Okay, so the error function for linear regression is given by 1 over 2 summation n is equal to 1 to capital N W transpose phi of xn minus Tn, the whole square. Okay, now what would be the gradient here? So what is del E of W? You differentiate this once, right? So you're going to get summation n is equal to 1 to capital N W transpose phi of xn minus Tn times phi of xn. Right? So if I write this in a compact matrix vector or vector form, so then the gradient is given by phi transpose phi w minus phi transpose t. Instead of summation, I'm just converting everything into vector. So I get phi transpose phi w minus phi. Okay. Why did I do that? Now it's going to be easier for me to differentiate this once again. So if I want to compute the Hessian is given by the gradient of the gradient. Okay. Which is simply phi transpose phi. Right? When you differentiate this equation once again, you get phi transpose phi. So if I have to write my Newton-Raphson update rule, right? It's going to be W new is equal to W old minus H inverse of the gradient. So it's going to be W old minus the Hessian was given by phi transpose phi, right? So phi transpose phi inverse. Then the gradient was given as phi transpose phi W old minus phi transpose T, right? So this becomes W old minus W old, because phi transpose inverse and phi transpose phi cancel each other, plus phi transpose phi inverse phi transpose T. So you can cancel these things. And in the case of linear regression, if you try doing Newton-Raphson actually converges in just one step, and you get your closed form solution. So now you see the power of Newton-Raphson, right? Like, so with gradient descent, you need to do many steps to converge, right? for linear regression. However, for linear regression, if you do linear regression, it directly gives you in one step the optimal solution. Okay. So this is actually because you have a quadratic objective. When you don't have a quadratic objective, like you will not get it in one step. Logistic regression doesn't have a quadratic objective, right? So then the linear regression is also going to take more steps. It is just that it's going to take much lesser steps when compared to gradient descent. Is that clear? So when you have a quadratic objective, you can reach the minimum in just one step with Newton-Raphson. So we're going to use this to understand gradient descent and Newton-Raphson, or compare gradient descent and Newton-Raphson. So based on their geometric views, okay. So I'm going to do gradient descent versus Newton-Raphson. Okay, so geometric view. Okay. So let's say I have a function like this. Let's copy the function twice just to have consistent picture. Okay. So if I have a function like this, whenever I do gradient descent, so the way in which gradient descent works is you start somewhere, you compute the gradient. So the gradient is telling you the opposite direction. So you do minus alpha times gradient, right? So then you take a very tiny step to reach here, right? So then you do another step. Then you do another step. So you're going to continue doing this for many, many, many steps. And finally, you'll reach the beginning. Right? Now, what Newton-Raphson is trying to do is, if we go back to the Taylor approximation, right? It's actually making this assumption that, well, not it's making an approximation of the error function to be quadratic. Your error function might actually have higher order degrees, right? You're just approximating your error function with a quadratic function. It is an approximation. Okay. However, this approximation helps you to move faster because once you make the quadratic assumption, Newton-Raphson will reach the solution of this quadratic assumption in one step. Right? So how would that look like? So in the figure, let's say we start at the same point, right? So Newton-Raphson is going to make a locally quadratic assumption or approximation. So it's going to approximate this function with a function, okay, that is locally quadratic. And it is going to find the minimum of this function in one step. So in just one step, gradient descent will move from here to here. Okay, so the minimum of this function is here, the approximation. So when you point it back to the true function, you're actually reaching here. Nice, right? So you, in one step, you're actually making a huge jump. So then you do the same process again. So you're gonna like make a quadratic assumption here, okay, and so you'll reach here, and you do the same thing once again. So you make another quadratic assumption. Okay, you make another quadratic assumption here, and you reach here. So with much less number of steps, you reach the minimum with Newton-Raphson. Is it clear? Any question? Okay, so maybe let's take a 10-minute break.